Welcome friends once again to my NPTEL MOOC module on exploring healthcare survey data. We are on the 7th week explaining panel survey data. This is the lecture meant for random effect model. In the previous lectures we explained very clearly about understanding fixed effect model in healthcare. Without explaining for further details on the previous lectures, I think it is time for the random effect model. It is based on the distribution of the panel data, and usually there are different forms of data in cross sections. We have different forms. We need to test whether it falls under fixed effect model or under random effect, and accordingly we take the appropriate decision. So, the random effect model is important because of some drawbacks with the fixed effect model. One of the drawbacks of the fixed effect model is its failure to identify any components of beta corresponding to the regressions that are time invariant for a given individual. Okay, so the beta which are actually also having some issues of time invariance, so are actually not discussed correctly in the earlier model. So, and accordingly we take off the estimation of beta based on the time component. So, there are some assumptions of random effect model. The assumption here is that the individual specific effect is a random variable, that is of course uncorrelated with the explanatory variables. Hence, the covariance of the covariance between alpha I and the XIT, the explanatory variables are actually equal to, the covariance is equal to 0. Okay. So, it is assumed that alpha I are random factors independently and identically distributed over individuals, and hence treated as the error term of the distribution. So, we will also combine those alpha component into the error term while estimating the random effect model. That is going to be shown in our slide. A random effect model handles the constants, that is the individual effects for each cross section, not as the fixed component, rather as a random parameter. If we have reason to believe the differences across entities and have some influence on your dependent variable, then we should use random effects, okay, instead of a fixed effect. The standard model of random effect is presented here, that is the dependent variable is with I.I.T is equal to the constant term with the beta coefficients and its explanatory variables. Okay, and at the end we have two component, that is the alpha I component and the error component. So, but both are we have already said that they are actually independently and identically distributed. So, alpha is distributed with its mean alpha and standard deviation sigma square, and the error term is actually is distributed with its mean 0 and standard variance. Okay, thus the random effect model can be actually composed with this error term, since they are independently and identically distributed. So, the alpha I content and the error term, both the components are actually capsuled with VIT, okay, and rest we are going to estimate. So, VIT is in fact the error term which is presented here, okay, and that consists of two components as alpha I and epsilon IT, which is the combined time series and cross section error component. Because of composite error term, the random effect model is also known as error component model. Okay, this is also known as error component model. Okay, in short it is called ECM. All right, and the alpha I are assumed as independent of the error term, and the XIT which are also independent of each other for all I as well as all T. or T component. This assumption is not necessary in the fixed effect model. So, this is how it is different as compared to the fixed effect model. So, the covariance of alpha I.T and alpha I.I. S is equal to alpha I.T and the covariance of epsilon I.T and the epsilon S is nothing but equal to 0, and we indicate that the individual difference arise from a common intercept, that is alpha naught, are same for all cross sections, okay, cross section units and also over time, and the alpha that varies cross sectionally, but not by time, okay, or time invariant. So, the covariance by after composing both this term error with its time component, error its cross section component. So, the covariance of VIT and JS is equal to VIT and JS should equal to the expected value. Basically, when we find out the covariance, we take the expected value of these two are actually equal to 0 or is equal to 0. So, the random effect model is estimated by a generalized least square technique in short called GLS, when variance structure is actually known. That is one of the important aspect. When that distribution is known, then we explain it through the GLS model, and by feasible generalized least square technique as well, insert that is called AFGLS, when the variance is not known. So, there are two approaches, one is when variance is known and when variance is not known, and accordingly GLS or FGLS models are actually used. We are also going to show you some practical explanations using the given data set. We will first estimate the random effect model using the command xt reg command xtreg. With the options, we will give it as RE random effect, and then we will find out whether that is actually fit or not. Okay, so we will go to the practical session. All right. Now, here is our data, and we will also use the same HO data which we already experimented in the previous lecture, and it is in our screen, and we are taking a WHO balanced data set as given, and accordingly we specified the way we defined. Now, we are also giving you the details on our screen. That first will operate with will set the ID variable and the year variable in our on our screen, and this is already set. The xtset command has already identified that it is a strongly balanced data, and the data is from 93 to 1997, and now we will go by the second command. The second command is to attach with xtreg the way we do, and at the end we will give the option as RE not the FE, okay, not fixed effect. So, this is our result, and now you can see the model is actually significant, and the implications impact of each of the component is defined, and its level of significance are also defined. You can easily read between the line, and these are positively linked to the dependent variable. Okay, so and I am not explaining much, I have already explained earlier in our previous lecture. Now, another aspect is that you can also add the robust option to control for the heteroscedasticity. If there is any technique you wanted to go for to check this heteroscedasticity, better to run with the robust option. This is the one we have already derived on your screen, and I have already explained about this, and similarly all those variables. Some interpretation also we attach here for your reference. Similar approaches we did it in our previous lecture. Another aspect is that the difference across units are actually uncorrelated with the regressors. That is that is also important.
So, this is mentioned here on the screen. You can see this is assumed to be 0 as per the random effect model. Okay. So, rest interpretations are perfectly fine and you can actually do it. Now, we are going to clarify whether our data is going to be interpreted with fixed effect model or random effect model, or we cannot just take randomly with any of the model. So, we need to specify with a test called Houseman specification test. This compares fixed effect and random effect models under the null hypothesis that individual effects are actually uncorrelated with any regression in the model. Okay. So, that is it is very clearly spelled and we already said individual effects are uncorrelated with the regression. It uses that the covariance of an efficient estimator with its difference from an inefficient estimator should be 0. If there is no correlation between regressors and effects, then fixed effect and random effect are both consistent, but fixed effect is in fact inefficient. If there is correlation, then FE is consistent, therefore, RE is not suggested to be applied. It is a test of the null hypothesis that random effects would be consistent and efficient against the alternative hypothesis that random effects would be inconsistent. The Houseman test has a specific chi-square distribution with as many degrees of freedom, okay, and as there are predictors in the model. If the p value is insignificant, that means the assumption is not rejected. Okay. If insignificant, that means if it is greater than 0.5 as per the standard practice 0.05, this means it is probably safe to use the random effects model. So, since the assumption is that coefficients not systematically distributed, difference in coefficients are not systematic. Okay. So, now it is not rejecting. So, if it is, since the assumption is that it is not systematic, that means it might follow randomness in the relationship between covariance is going to be 0. Now, this is not rejecting, that means in this case in our result also we can check. These are the command you can easily see. I will also operate with it. We will first go by the extract with fixed effect, then we will estimate and store that fixed effect result. Okay. We will store it, then we will go for random effect model, okay. Then also we will store, then we will check Houseman test. Okay. So, this is how it is followed. You can have a check. It is here. Okay. Now, we have this. First we will run with once again with fixed effect with the same data set. Then we will this is the fixed effect result and we have already interpreted this. Okay. And earlier, and you can check, you can store this fixed effect result, estimate, store, fixed with the name fixed we have given. Okay. Then we will run the random effect model and we will also store it, store with the name random. Okay. And we have stored it. Then we have run the Houseman test. Houseman test is the most suggested instrument to check the difference. Okay. Now, you can see that your hypothesis is that it should not be systematic. Okay. The difference in coefficients not systematic. Okay. So, systematic means it follows certain order, not systematic means it is having certain randomness. All right. Now, it is saying that the randomness is not in fact rejected because of the p values. You can see the p value is of value 0.3061. That means it is greater than that of 0.05. So, it is not rejected. This model is not rejecting the null hypothesis. That means it says that it is in fact non-systematic. The covariance is expected to be 0. Therefore, it is suggested to go for a random effect model instead of fixed effect. Had it been the fact that it is this p value is significant, it is always suggested to go for a a fixed effect model. All right. Now we can see here, and these are all presented on your screen. Even I have clarified using this screen. Okay, so let's move for another comparison. Constant common model as compared to the random effect model. So one of the tests that is important in this case, which is frequently used by the researcher, is called Grosspagan Lagrange multiplier. In short, it is called LM test. Okay, LM test helps to decide between a random effect and a pooled OLS. So pooled OLS, which we have already said for CCM, constant common multiplier or model. In that case, we have a comparison in this particular segment, that is the null hypothesis in the LM test is that. Likewise, we did for the Houseman test. Here also there are certain null hypotheses. This suggests that variances across entities is 0. Variances across entities is 0. This is no significant differences across units. Okay. So across units there is no significant differences. That means there is no panel effect. All right, that is the assumption. If it is violated, then accordingly we can take the decision. Here is the command, like you have to go with the extract, then random effect. Then the next text is test 0. Here this gives you the idea that here the label is significant, the p value is significant. This suggests that we reject null hypothesis and conclude that random effects is in fact appropriate. Okay. Based on the likewise assumption, it suggests that the variance across entity is 0 and no significant difference across units. But here you are saying it is rejecting that one, and accordingly we take the decision. This is what you can also check it. We have kept everything over here. Okay. So this is the one, we have run it on your screen, and you can just have a look. All right. And here is the level of significance. And since it is significant, so it suggests that you should go for a random effect model instead of CCM one. All right. Then it comes for understanding whether there occurs any cross sectional dependence. It might be the case that the cross sectional units are also dependent to each other. Okay. So for that Passerine CD or cross sectional dependence test, CD in short, this test is used whether the residuals are actually correlated across entities. The residuals we have are actually expected to be correlated. Then cross sectional dependence can lead to bias in test results. So the null hypothesis suggests that residuals are not correlated. Okay. So if they are correlated, then we have to take the decision accordingly. Like here, our p value, the probability value for it is actually suggests that it is having a value 0.0761. Now we can see that there is no cross sectional dependence, okay, because of its level of significance. And the command for this test is XTCST. All right. If not available, then we need to actually install it by typing SSC install XTCST. Okay. So that we can do it on your own. It is on the screen. XTCST. So you need to install it. We can take the help of this. Okay, so SSC install XTCST. SSC. All right, so it is okay. Okay, verifying not already installed. So now installation is complete. Now you can take the command and accordingly we can take the decision of running it. Okay, so this is the both of this we are actually running it, and we found that this is actually significant and there is no cross sectional dependence. All right, and now this is done. Then another possible aspect is to also check with the serial correlation, because of the time component. So, serial correlation causes the standard errors of the coefficients to be smaller than they actually are, and higher R square is possible. So, we need to check. So, XT serial command available to test serial correlation. So, XT serial we need to search this XT serial, then net SJ 321, and then based on the string value of it, then accordingly string, since it is the variable code is in string, so accordingly we can do it. I am just going to show it over here like this. These are the command. Okay, so basically what I am saying, we need to install the program. We need to search for XT serial, then net SJ 3-2 ST 0039, then we need to install that particular ST 0039 on our system. So then only it will work. Okay. So now this is being searched, and we will XT and next one XT 0039. So this is we need to install it. Okay, and once it is installed, yes, now it is complete, we can run that command. The command is to understand the serial correlation. So that is basically SSC install, we did it, then xtrag, we need to compare these three. Okay, so now we have got the result on your screen. You can see that these three steps you have to follow it, and everything is on your screen. Even we have also kept all those things systematically. Now XT serial, the two variable we have taken. Okay, and now basically this is also called as Aldrich test for autocorrelation in panel data. Autocorrelation in panel data, and the hypothesis there is that there is no first order autocorrelation, and since it is significant, that means there is serial correlation, first order serial correlation exists in the data. Okay. So now this is the one to see if time fixed effects are needed when running a fixed effect model. We need to use the command test parm. Okay. So based on the serial correlation, we can identify whether there exists serial correlation or not. Next one is to understand whether it has certain time fixed effect or not. So the command, standard command we take is called test parm. So null hypothesis in this context is that the dummies for all years are equal to 0. Okay. So the dummies those are taken are for all the years of the dummy are actually equal to 0. So the command is in fact we have taken here as I dot as the dummy. Okay, for all the years dummies are equal to 0. So test parm I dot year we have taken, and based on that we can see that the probability value p value is greater than 0.05. We will also see that. So in this case that we fail to reject the null hypothesis, therefore no time fixed effect are needed in this case. You can also check it with the data. This is presented in our do file as well. So here is the do file. You can run the do file to understand the time fixed effect, and so we find that we can see in the result that it is not significant. So, there is no time fixed effect, okay, in the model. All right, and no time fixes are needed in this case. Therefore, we can ignore that, and it is not necessary to run further. After saying all those basic or important steps in random effect model, we have guided with the help of the WHO balanced data example data set. You can also run on your own through the ISDS data set example data set we have already uploaded on your screen, and that is given with the name practical instata. Dependent variable is medical out of pocket expenditure, and that is in rupees, and the independent variables are given as annual household consumption expenditure, that is proxy of income, and then religion, etc. Religion is the ID variable. Okay. You can just check these. I am not experimenting. We have already given everything on your folder, and for your easy operation, we are keeping this data set for you to understand random effect healthcare, random effect panel data in healthcare. So, these are all here for you. We look forward for your participation in the next class. Thank you.